Okay, question one. And these are multiple choice answers. All equations that I'll be using will be derived from the formula sheet that we're given. An object is moving to the right with speed vi when a force of magnitude F is exerted on it. Which of the following situations is the object's direction of motion changing in kinetic energy in decreasing at the instant shown? So basically, what they're asking is for a change in kinetic energy. And because our mass isn't going to change anytime soon, a change in kinetic energy means change in velocity. So with example A right here, oh, and the direction of motion changing is obviously if um, the this vector right here is changing direction. So essentially, we want to we want something, a force that will change the magnitude, which is given in this kinetic energy equation, and the direction. So because the force is applied perpendicular, the magnitude of the velocity in question in part in option A doesn't change at all actually. The velocity is going to be staying the same because it's perpendicular. We are not going to have a change in velocity. Now, for option B, we do not have a um, change in direction. It will slow down, and it's at the instant shown, right? Eventually, the force will cause the velocity to change and to go the opposite direction, but in the instant being shown, we don't actually have a change in direction. We only have a change in kinetic energy or magnitude of the velocity. So option B isn't an option either. Option C, while we are changing um, the direction and we are changing the magnitude of the kinetic energy, we're not we're not decreasing um, the kinetic energy of the system. Because the horizontal component of the force is in the positive direction, we're actually going to be increasing. So it's not going to be option C either. Now, because in this one, the horizontal component of the force is away from the direction of motion, um, and it's at an angle that's different. It's not parallel or perpendicular or anti-parallel or anything to the direction of motion. So we're going to go with option D here. Question number two, a ball suspended by a lightweight string as shown as figure above. The ball is displaced to position one and released. The four labeled positions are evenly spaced along the arc of the ball's motion. Between which adjacent pairs of positions is the change in the kinetic energy of the ball the greatest? Now, this question is deceptively simple. Now, all these arcs are equally spaced in length. So what it comes down to is the greatest change in kinetic energy. Well, what is our change in kinetic energy? We're again given the same formula. Kinetic energy is 1/2 the mass times the velocity squared. So think about it just for a minute logistically. We have a potential energy right here. Our potential energy is given by mass times the gravitational accelerational constant times height. Now, if we look at this system, we have it released and it's suspended here. We have it released and it's dropping downwards. And because of that, it's accelerating. So our between each length, our velocity is actually getting greater. Um, and if you think about it, because the velocity is squared, the larger the change in the velocity, it's going to have a drastic change on our kinetic energy. So if you think about the ball, it's gaining traction here between 1 and 2, it's speeding up a little bit more, and then between 3 and 4, it's just going to town. It's going super, super fast. So in this instance, we're looking for the greatest change in kinetic energy, which is going to be determined by the greatest change in velocity, which would be at this bottom part between 3 and 4. Sweet. Now, this one is also a really tricky one. Where newly discovered planet is found to have a density two-thirds the density of Earth and radius twice the size of Earth. And these constants here are the density and radius of Earth, respectively. The surface gravitational field of the planet is most nearly, okay, when we're talking about surface of the gravitational field, we're talking about G, right? It's defined as the force of gravity over mass. That's an equation that we're given from our sheet, right? It's something that we all know off the top of our head, Fg equals mg, right? But for this instance, um, we're used to having our g as 9.8 or in for the AP, a lot of the times they'll tell you to round it to 10 to keep things simple. But because we're on a different planet, things are going to be a little bit different. So let's write out the universal law of gravitation. Um, Fg equals m1 m2 times g all over r squared. So what we can end up doing is, because we want to solve for g, we can divide both sides by m and actually cancel out one of the m's. So we can get from here, we can get g equals m, and in this instance, it's just the mass of the Earth, um, g over r squared. We also know that density is equal to mass divided by volume. And so instead of m, we can substitute density times volume. But what's the volume of a sphere? Volume of a sphere is 4/3 pi r squared, or pi r cubed, excuse me. And so, substituting all of this in, we get density times 4 over third over 3 pi r squared all over r squared. Cool. Now, because of this, our r cubed cancels with the r, just leaving one r. So we can write it as density 4/3 pi r, and this is going to be for our gravitation. Now, we're given 2/3 the density times um, times twice the radius. And so once we plug all of these values in, um, we get 2/3 times 4/3 times pi times 2. Oops. That's a pretty large 2. Um, and when we multiply all these things together, we get about 1.7 newtons per kilogram. And if you think about it, this actually physically makes sense because G is defined as the force of gravity over the mass of the object. And we have as our units newtons, force, and then kilograms for our mass. So this one would be option A. Number 4, a bus initially traveling south at a constant speed is shown in the figure above. As the bus starts to make a left turn without changing speed, a passenger notices that a box on the floor starts sliding toward the right of the bus. Which of the following views of the box, when correctly labeled, would best represent all of the horizontal forces exerted on the box as it is sliding? Um, so think about the box moving on the bus. It's causing it to go and move to the right, but there's also friction between, we're not told that it's frictionless. And so because we're told it's not frictionless, we can assume that there is actually friction. And this one's pretty easy actually because D is the only one with a frictional force. Remember, this is the friction of the box on the floor that's resisting the force of motion, and then this is the force that's pushing the box to the right. Beautiful. Okay. Questions 5 and 6 are based on this diagram. Three identical plot blocks each take a different path from height h to the ground. Block A is released from rest, falls vertically. Block B is released from rest and slides down a frictionless incline. Block C is projected horizontally with initial speed v. Cool. So let's break down each of these examples. In this one, this is a simple this is a simple acceleration, so its acceleration in the y direction is going to be g, negative 9.8 meters per second per second. With this, going down the incline, we know that um, mg sine theta points down the incline. And again, you don't have to know this off the top of your head. It's helpful to know mg sine points down the incline. There's a whole derivation you can do also with labeling um, the perpendicular and parallel forces of the incline as opposed to the force of gravity. Um, you can draw out a triangle with the free body diagrams and all that. We won't go through that because it's a pretty lengthy process, but know that because it's at an angle, it's going to be a component of the force of gravity, mg. And so because this is an angle that's less than 90 degrees, sine 90 is 1. It's going to be less than 1. So this is going to be only a part of the force of gravity that's pushing it downwards. Um, it's like the difference between going down your bike on a hill versus going just going off a cliff and traveling that same height. It's quite a bit of difference. Your acceleration going down that hill with is going to be a lot different. And then with this, we know that the horizontal velocity in the x direction, if we're told that there's no air resistance, um, is going to be the same. So the initial velocity is in the x direction, but because it starts because it starts from rest, the y component of the velocity is going to be decelerating in the y direction. So which block takes the longest time to reach the ground? Um, Block A and Block C are going to reach the ground at the same time because they're limited by their um, by their acceleration in the y direction. It's exactly the same. It doesn't matter that Block C is traveling in the x direction. All that matters is when it hits the ground. And blocks A and C are going to hit the ground at the same time. Block B is going to take a little bit longer to hit the ground because it's the force of gravity is um, being applied at an angle in this instance. There is no friction on the incline, which is nice, but this still means that it's going down at a fraction of the force of gravity as opposed to A and C. So block B takes the longest time to reach the ground. Which block has the greatest speed just before hitting the ground? Well, if we draw a vector of um, all the speeds, block A's speed is going straight down. Block B is going to hit the ground at a speed like this. And remember, it's the magnitude of the acceleration is given by mg sine theta. So it's going to be a fraction of the speed it would have been if you just dropped it. Then with block C, in addition to the force of gravity, you also have this initial x velocity in the x direction. And so with block C, you'll have the y component be exactly equal to the y component for block A. But because you already have this velocity in the x direction, it'll look probably not the most accurate. It'll probably look um, something like this. It'll be the exact same, it'll be the exact same magnitude as the y version of block A, but in addition, it'll have the magnitude of the x direction. So C will have the greatest speed before hitting the ground. Cool. Ball dropped from rest falls to the floor. Um, the initial gravitational potential energy is of the ball earth floor system is 10 joules. The ball bounces back up to the height where the gravitational potential energy is 7 joules. Okay, it looks like we lost some energy in the collision with the earth. So here in this instance, we lost about 3 joules to the ground. What is the mechanical energy of the ball earth floor system the instant the ball left the floor? So mechanical energy is defined as potential energy plus kinetic energy. So the second the ball, I'll write it as this, ME equals KE plus PE. So the second that it leaves the ground, it's going to be mostly kinetic energy because as right when the ball hits the ground for the first time, it has the greatest kinetic energy, but we lose some of that. Um, we lose some of this to friction, which isn't technically part of mechanical energy. Some of this total energy gets lost to outside forces, whether it's heat or friction or something else, and we get these 7 joules. But the second the ball leaves the floor and there's that end of that contact, the ball still has 7 joules because that's a measure of the potential energy. When the kinetic energy is 0 and it bounces up to a height of 7 joules. So the instant the ball leaves the floor, it's still going to have a a total mechanical energy of 7 joules. It's cool. Um, a disk is initially rotating counterclockwise on a fitted axis with an angular speed omega naught. At time t0, the two forces are shown in the figure are exerted on the disk. If counterclockwise is positive, okay, that's good to know. They love to trip you up on the AP exam with the different directions. So I'll draw a big arrow that counterclockwise is positive and clockwise is negative. Which of the following shows the angular velocity at disk of the disk as a function of time? So this one looks right, right? It's initially starting in this direction, but it's starting negative and not positive. So doesn't this isn't right because it initially starts in the positive direction. So we need a graph that starts above the x-axis. So this one is not right. This one is not right either because the velocity is changing. It's not the angular velocity is changing. It's not constant. This one decreases, and eventually, because the force in the clockwise direction is greater, it'll actually start going in that direction. So this looks to be our most accurate. And just to check, just for kicks and giggles, this one, it stops and then it speeds up back to its initial speed. That doesn't really make physical sense given what we're working with here. A 50 Newton box is at rest on a horizontal surface. The coefficient of static between the box and the surface is 0.50. The coefficient of kinetic friction is 0.30. And horizontal 20 Newton force is then exerted on the box. The magnitude of the acceleration of the box is most likely. Cool. This is a easy peasy lemon squeezy problem. We're given that the force of force is equal to magnitude times acceleration. We're also given that the force of gravity on the box is 50 newtons. And divided by 10, which is the gravitational accelerational constant, we get the mass is about 5 kilograms. Remember, mass is in terms of kilograms and not newtons. Newtons is the force of gravity that's being exerted on the box. So we are given, as part of our equations, F divided by m is equal to a. So that's going to be the magnitude of the acceleration. But wait, there's also the force of friction pushing in the opposite direction. The force of friction is equal to um, the normal force times the coefficient of friction, not equal to, times the coefficient of friction. And because it's moving, because we're talking about acceleration, we want it to be the kinetic coefficient of friction. And it's actually pretty convenient for us because the normal force is the force of the ground pushing on the box to compensate for the weight of the box. And the weight of the box we're actually given in our equation, which is pretty nice and easy. So we can write the force of friction as 50 times zero point 0.3. Now all we need to do is find the acceleration of the box. So finding the sum of all the forces, we get acceleration is equal to 20 minus 50 times zero point 0.3 all over the mass, which is about 5 kilograms. So if we punch that into our handy dandy calculator, we get 50 times zero point 0.3 is about 15. The, so 20 minus 15 is 5 divided by 5 is 1. So our acceleration is 1 meter per second per second. And this last one is also looks hard, but it's actually really, really easy. So we know using a thin rod of length d on a frictionless surface is pivoted about one end as shown above and can rotate freely. The rod is at rest when it is struck by a sphere with linear momentum of magnitude pi perpendicular to the rod. The sphere rebounds along its original line with line of motion momentum of magnitude pf. What is the magnitude of the angular momentum of the rod immediately after the collision? So we know, given the conservation of momentum, that P before, our momentum before, is equal to the momentum after. And those symbols just mean the sum of all the momentum. So the only momentum in this first part, this will be our before, and this will be our after. So the only momentum that we have here, because this thing is at rest right here, the only momentum that we have is our pi, because P, that looks more like a rho for density. P equals mv. And so because we only have this thing here, um, because it's not moving, because the velocity is 0, our only momentum in the system is our pi. So we can write on the left side of the equation pi, and then we have two sources moving here. We have the rod is moving in a circular motion. So this is going to be our angular momentum is with the rod. And then our linear momentum is with the ball here in the opposite direction. So we'll write it as L minus PF. And angular momentum is symbolized by the letter L. So we can solve for L, and it's PI plus PF. This one is nice and easy. Anyways, hope you enjoyed those problems. Thanks for sticking along with me. And be sure to reach out and email me if you have any questions. Thanks for watching. Have a good one.